Ever get the feeling there's more to something than meets the eye?
Like you stumble upon a topic and you think, oh yeah, that's simple enough, but then you start digging and whoa, it's a whole rabbit hole of complexity.
Right. Today's deep dive is a perfect example. We're tackling whole numbers.
Whole numbers, you mean like 1, 2, 3, sounds pretty basic.
Exactly. We're using these excerpts from what looks like an educational text to guide us. And believe me, there's more to these numerical building blocks than you might think.
Okay, I'm intrigued. You've got me thinking, what exactly is a whole number?
Well, we're talking 0, 1, 2, 3, on and on the counting numbers, but zero's invited to this party.
And our source jumps right into visualizing these numbers. Picture a number line. It goes on forever in both directions.
Like a ruler that never ends. I remember those from back in school.
Exactly. It's a simple tool, but it helps us see how whole numbers relate, kind of like a map, but for numbers. Plus, we can visualize stuff like addition or subtraction.
Oh, I'm curious about that. How does that work on a number line?
Let's say you want to add 3 and 2. You'd start at 3 on the line. Then, since you're adding, you move 2 spaces to the right, and boom, you land on 5.
So instead of just memorizing 3 plus 2 equals 5, you're seeing it in action. That's pretty neat.
It's a great way to make it click, especially for visual learners. And, this leads to something fascinating about whole numbers. They have these built-in properties, like a set of rules. One is the closure property.
Rules. Okay, now you've really got my attention. What's this closure property all about?
In simple terms, it means if you add any 2 whole numbers, the answer is always another whole number.
That makes sense.
Yeah.
7 plus 8 is 15, which is still a whole number. But what about subtraction? Like 7 minus 8, you get -1, and that's not a whole number.
You've hit the nail on the head. Closure works for addition and multiplication of whole numbers. But subtraction and division, well, not so much.
So the rules change depending on what you're doing. This is getting interesting. Now, the source also mentioned something called the commutative property. What's that one all about?
Think of it like rearranging furniture. You've got 6 rows of 8 chairs. Rearrange them into 8 rows of 6. Same number of chairs, right?
Yeah, just a different setup, but same total.
Exactly. That's what the commutative property means. When you add or multiply whole numbers, the order doesn't matter. 3 plus 2 is the same as 2 plus 3.
Handy trick. Are all these properties that straightforward? I remember struggling with the associative property back in school.
It sounds more complicated than it is. It's about grouping. Say you're adding 2, 3, and 4. The associative property says we can group those numbers however we want when we add them, and the answer stays the same.
So I got to add the 2 and 3 first, then add the 4, or add the 3 and 4 first, then add the 2. Either way, I get 9.
Exactly. And this isn't just a mathematical curiosity. It can be super useful. Like our source talks about multiplying 8, 1769, and 125. That's a mouthful to calculate, but if you rearrange them using the associative property, it gets a lot easier.
So it's like a mental math shortcut. Man, I could have used that back in the day. There's another one, right? The distributive property. That one always sounded mysterious.
It's incredibly powerful. Our source uses a graph paper example to show it. Imagine a rectangle on graph paper. It's 6 squares high and 8 squares wide. To find the total number of squares, you multiply 6 by 8.
Right, 6 times 8, which is
48. But here's the distributive property in action. Instead of 6 times 8, we split that rectangle into 2 smaller ones, one that's 6 by 5 and another 6 by 3.
I'm picturing it. So you're breaking down the 8 into 5 plus 3.
Exactly. Now, find the area of each smaller rectangle, add them together, and you get the same answer. 6 by 5 plus 6 by 3, which is 30 plus 18 equals 48.
So the distributive property helps break down big multiplication problems into smaller, easier ones. That's super handy.
Exactly. Think of it like this. You're buying 6 sandwiches, each costing $8. Use the distributive property to find the total cost. 6 by 5 plus 6 by 3, which is $30, plus $8 equals $48.
I'm starting to see these properties less like rules, more like superpowers. They're tools for working with numbers, whether it's equations or figuring out lunch money.
And there's one more property we can't forget: identities.
Oh, right. Like 0 for addition and 1 for multiplication. They don't change the other number when you use them.
You got it. They're like the anchors of their operations. Super important in the world of whole numbers.
This is way more interesting than I thought. Who knew whole numbers had so much going on? And we're not even done yet, are we? Our source also talks about some fascinating patterns within whole numbers.
Oh, absolutely. And those patterns, even more surprising and fun than the properties themselves. Get ready to see a whole new side to whole numbers. Ready to dive in.
You know those visuals in the source material? The ones with the dots arranged in patterns, those really caught my eye.
Arranging whole numbers geometrically, it's a really cool way to visualize them. Some numbers, like prime numbers, they can only be arranged in lines, but others, like square numbers, they form squares. Makes sense, right?
And then there are triangular numbers, forming perfect triangles. The source even challenged us to figure out which numbers fit into each category.
It's a fun brain teaser. It shows how numbers are structured, how they relate to each other. But those visuals, just the tip of the iceberg. Our source also talked about some super practical patterns like adding or subtracting numbers like 9, 99, 999, that sort of thing.
Oh, the shortcuts. Instead of calculating 1017 minus 9 directly, you'd subtract 10, then add 1 back. So 117 minus 10 is 107, plus 1 equals 108.
Exactly. It seems a bit weird at first, but think about it. 9 is just 1 less than 10. So subtracting 10 and adding 1, it's like a sneaky way to subtract 9, like
Yeah.
easier to do in your head. And it works for adding those numbers, too.
Mental math hack. Way better than getting bogged down with all those nines. Why didn't they teach us this in school?
And there's more. Remember the distributive property. Understanding that 1 unlocks even more mental math shortcuts, especially when you're multiplying by 5, 25, 125.
Oh man, I used to struggle with those. Multiplying by 5 always felt harder than it should be.
Get ready for this. Instead of multiplying by 5 directly, multiply by 10, then divide by 2. 10 is twice as big as 5, so dividing by 2 gets you the same answer in the end.
So for 96 times 5, instead of doing that, I could do 96 times 10, which is 960, then just divide by 2 to get 480. So much faster. Does that trick work for 25 and 125 too?
You bet. It's all about seeing the relationships. For 25, you'd multiply by 100, then divide by 4, because 100 is 4 times bigger than 25. And for 125, multiply by 1,000, divide by 8.
These patterns are blowing my mind. It's like there's a whole secret code to numbers that we don't always see.
That's what makes this so fascinating. We've got these properties, these patterns, and they all connect. Remember the closure property? Turns out it's closely tied to those visual patterns we talked about.
Oh, how so?
Well, think about it. Adding whole numbers always gives you another whole number, right? That's reflected in how we can arrange them into those geometric shapes. Each shape shows a specific set of whole numbers and their sums. Like those triangular numbers, they're all formed by adding consecutive whole numbers.
So the first triangular number is 1. The second is 1 plus 2, which is 3. The third is 1 plus 2 plus 3, which is 6.
Exactly. And the fact those sums always give you a whole number. That's the closure property in action. It's the same idea from different angles.
This is incredible. It's like we keep peeling back layers, and there's always something new to discover.
And we're not done yet. There's still so much more to explore.
This whole thing has been eye-opening. It's like we're uncovering a whole new side to whole numbers, going beyond just their basic quantities.
It's about seeing them as the building blocks they are, with their own rules, their relationships, even their little secrets.
And speaking of secrets, our source really emphasized the role of 0. It seems so simple, almost easy to overlook, but it's crucial for the whole system.
The unsung hero of the whole number world. Think about it. It's the additive identity. Add 0 to any whole number, nothing changes.
And multiplication, too. Anything times 0 just becomes 0. It's like 0 can either leave things alone or totally wipe them out, depending on how you use it.
It's a good reminder that even the simplest things can have a huge impact.
This deep dive has totally changed how I think about whole numbers. I'm seeing them in a whole new light.
And we've only scratched the surface. We've explored these properties, these patterns, all these connections. But there's so much more out there. This is just the beginning.
So even though we're wrapping up this deep dive, the exploration doesn't have to end here?
Absolutely not. Remember those triangular numbers we talked about? The ones that form perfect triangles? I challenge you to dig a little deeper into those. See what you can discover.
I love it. We're leaving our listeners with a challenge, something to ponder.
Exactly. There's always something new to discover in the world of numbers.
And on that note, we've reached the end of our deep dive into the fascinating world of whole numbers. We hope you enjoyed this journey as much as we have. Until next time, stay curious.